Hi everyone. So yesterday I asked you to complete the write-up for this experiment by watching the video online, and I'm just going to take you through the calculation that's in this experiment. So the experiment is called to determine the heat of reaction of hydrochloric acid with sodium hydroxide. The hydrochloric acid being our acid and the sodium hydroxide being our base. Remember, your heat of reaction is the heat liberated when 1 mole of the acid in this case will react fully with 1 mole of the base, and we can see it's a 1:1 mixture. This is all done in an insulated container. In this instance, it's done in a polystyrene cup. Now, the reason we do it in a polystyrene cup is that it's quite heat negligible. It doesn't take heat away from our reaction mixture. So we calculate the temperature difference and we calculate the heat of reaction. So a few steps to point out. It's obviously really important to use the same volume of acid and base to make sure that we're having an even test. So we would use 50 centimeters cubed of 1 mole of HCl, 50 centimeters cubed of hydrochloric acid. The second really important thing to note in this is that they both have to be roughly the same temperature before you add them in. So we would have poured them both out, let them settle for maybe 5 or 10 minutes in the classroom surroundings, and then very, very carefully we would have added the base to the acid. Now you want to do this slowly. You don't want to splash any base out, any acid out, and you want to gently mix the solution so that it's evenly mixed with your thermometer. And then you would place the lid on, so the polystyrene lid on top, and you would continue swirling, and you would do this for about 5 to 10 minutes again. And over those 5 to 10 minutes you would record the temperature, and the temperature value that you would use would be the highest temperature that you recorded during that time. So when you were doing the experiment write-up, I would have left this bit blank. So these are the results that we are going to use for this experiment. Our temperature before was 22. Our temperature of the HCl and NaOH were both 22 before, and the highest temperature reached after the mixing was 28 degrees Celsius. The temperature rise overall was 6 degrees Celsius. So to calculate our heat liberated formula, we use the formula m by c by delta T. So m stands for the mass in kilograms, c stands for the specific heat capacity, and this is given to you in the question, and delta T stands for the change in the temperature. So the temperature before, take away the temperature after. In this experiment, we assume that the density of the solution is the same as the density of water. So in total, we used 100 centimeters cubed, 50 centimeters cubed of acid and 50 centimeters cubed of base. So we assume it's the same as water. So in this instance, that's 100 grams. But remember, our mass value needs to be in kilograms. So we divide that by 1,000 and we're left with 0.1 kilograms. Our specific heat capacity for C, we also assume that it's the same for water, but like I said, this will be given to you in the question, is 4.2 kilojoules per kilogram in Kelvin. Next thing we need to figure out is our delta T. So delta T is equal to our temperature change. So our highest temperature that we reached overall was 28. Our lowest temperature was 22. So that gives us a delta T value of 6. We then take those three numbers and we put them into our equation. So we get 0.1 multiplied by 4.2 multiplied by 6, and that gives me 2.52 kilojoules. Now, don't forget, that's 2.5 kilojoules, 2.52 kilojoules per mole. But what we have to remember is we didn't actually use 1 mole, so now we need to figure out the concentration of our actual solutions. One advantage we do have, though, is that our moles of acid is equal to our number of moles of base. In both of them, we used 50 centimeters cubed of a 1 molar solution. So to calculate how many moles we actually used, we take our 1 mole and we divide it by what it's in. So capital M means moles per litre, and we divide it by 1,000 and we multiply it by 50, and that gives me 0.05. So now I need to figure out, well, what's the heat of reaction for my actual value. So to get our final answer, we take our 0.05 and we divide that by our 2.52 and we get 50.4. Now, the last thing that we have to figure out is what sign is it? Is it going to be negative or positive? It's going to be an exothermic or an endothermic reaction. So you can see that we had a temperature rise of 6 degrees. So that means heat was given out, and we know that that means it's an exothermic reaction. And if it's an exothermic reaction, that means my value has to have a negative sign in front of it. So final point is including your minus sign and your units in kilojoules. Very quickly, I'm just going to fly through some of the questions. So, what precautions are used in the experiment to minimize heat loss? Well, a polystyrene cup is used because the specific heat capacity of polystyrene is negligible. That means that it doesn't really take in any heat, nor does it lose any heat. And using the lid helps to keep the heat inside it also as well. Question 2. Chemistry data books give the heat reaction of 1 mole of hydrochloric acid with 1 mole of sodium hydroxide is minus 57 kilojoules per mole. Why do we think your answer is a little bit different to this? Well, there's a few things. When we were doing this experiment, more than likely we would have used a graduation cylinder. We know graduation cylinders can be a little bit inaccurate. If you were doing this in a real life lab scenario, you might use a pipette, burette, etc., etc. We only know the rough accuracy. So because of all of these assumptions, that was going to cause errors as well. The polystyrene cup that you used may not have a zero specific heat capacity. You may lose heat to your surroundings. The density of the acids and bases may not be exactly equal to the value for water. So in terms of what we do, there is several sources of error, but these are the particular areas that we focus on for your leaving cert experiments. And finally, guys, the third question, if 1 molar nitric acid is used instead of 1 molar hydrochloric acid, or 1 molar potassium hydroxide was used for sodium hydroxide, we get similar values. And why does this happen? So hydrochloric acid and nitric acid, they are both monobasic. So let's think about what that means. Okay, they both release one hydrogen. Okay, and they're fully dissociating water. Whereas potassium hydroxide and sodium hydroxide, they're both monoprotic bases, NaOH, KOH. They donate one OH minus ions. So in all the experiments referred to, the only reaction that's really occurring is between your H plus and your OH minus ion. And so that's why our heat of reaction ends up being the same.